Good morning. My name is Dale McKinney, and right now I'm doing heart disease prediction. It's going to use two different techniques, and this is for the same BDAN course. We're going to use the logistics regression model and a decision tree to predict the binary outcome of heart disease using the provided data that was in the Excel sheet. Okay, I need to upload the Excel sheet first, so we're going to go back here to Philip. And it is uploaded. I have already done that. Now we're going to import the heart disease data set. We're going to install the packages. As we're waiting on those to install, it'll be installing really quick. So now it's heart disease, and we're going to import this. It is imported correctly. So here's our R code built. So we're going to build and compare two models. So predicting heart disease, that's what lines 1 through 7, 6A. So let's go ahead and run those. Now we have to update some packages. Restarting our session. Let's download the source packages. So we're good there. So now we're going to move on to line 7, install the packages, and line 8, run the R plot. So the R package will be used to build a decision tree model, which we're going to do now. And then we're going to install the package caret. The package caret, I'm not sure if I'm pronouncing it right. It provides functions for data partitioning, creating training and testing sets, and well is an evaluation metric like a confusion matrix. Loading that all in. Then we're going to do the library. It provides functions and data partitioning in the library. So we've done all that. So now we're going to load necessary libraries. So our library R ports for a decision tree model. And our plot, it will be loading in for the visualization decision trees. And then we're going to do data splitting and evaluation on the library caret. So we're pulling from all those libraries now. Line 16, we're going to read the data and update the file path as needed. So we've done that now. So now we have our data and heart disease in here. We got 918 objects of 12 variables. And those are all loaded in. So that's good. Now what we're going to do here is we're going to convert the target variable to a factor, because we can't be running in binary code. It's really hard to understand. So we're going to create all those variables into, it's assumed to be coded as 0 and 1, and we want to run them in factors. Easier to read, easier for us to understand. Now 23 through 29 was, we want to set random seed for reproducibility, and we want to set the seed at 123. It's a random number generator seed so that the results are reproducible. And then we're going to split the data into training, and this function is going to generate row indices for 70% of training, while set while preserving the class distribution. So, we can see here 70% training and 30% testing, and it's going to still stratify the heart disease. So we're in that now. And, of course, the heart disease is that list is false. So we're going to train the data and test the data, which we've done there. And we come up here. We trained the data. We came up with 643 objects of 12 variables still. Our training data came in at 1643 and 1. So now we're going to run the logistic regression model. So on the logistic regression model, we're going to fit the logistic regression model using all predictors. So let's run that now. Okay, we did that. That ran fine. And the predictors in the family of binomial, their argument specifies the outcome of binary. So then we're going to run down here to print the summary. Now we're going to print the summary of the fitted logistic regression model, including coefficient estimates and statistical significance. So as you can see down here, we caught our binomial, and then we ran our coefficients, and it gave us a nice small thing down here: cholesterol, fasting, sleep slope. And then we ran down to print our summary. So our number of Fisher scoring iterations was 5. Now we're going to generate predictive probabilities for the test set. This is returns probabilities for a positive class of heart disease in 1. Now we're going to convert and the possibilities of class reproductions using the 0.05 cutoff. So, if you look here, predicting logibility of 0.05 is 1 and 0. So we need to run that factor. And then we're going to do line 46, which is also going to predict a factor as pre-logic. That converts the class label vector into a factor so that it can be compared with actual factors of the values of heart disease. Then here we're going to evaluate the logistic regression model with the confusion matrix. So that computes a confusion matrix to evaluate the regression model's performance. And now we're going to print it so we can see it. There it is. I like the print feature because it gives you a good view of what you did in your coding. So our predictions were 107.16, 116, 136. Our accuracy moved to 88.36 with 95%. So you go down here, and our positive class is 0. So it wasn't too bad. 88 with a 95% CI, it's okay. So let's run down to the decision tree model. And what we're going to do here is the decision tree model is going to fit the model to predict a heart disease using all predictors. The argument method, class, specifies that the model is for classification. So we're going to move that out. And then what we're going to do here is go down to the plot, the R plot. The plot's decision tree so you can visualize how the model splits on its predictors. So run that, and there's our model. Came in with our slope up. So now what we want to do is we're going to generate predicting class labels for the task set, which we did here. There we go. And now we're going to evaluate the decision tree model with the confusion matrix. So we're going to compute a confusion matrix to evaluate the performance of the decision tree model. And then we're going to print so we can see down below. There we go. So our accuracy of 95%, or 0.086. So as you can see, the predictably was 0, 1, 109, 24, 1, 14, 28, very similar. And now we're going to compare the two models. And the first thing we're going to do is we're going to look at comparison. So the logistic regression accuracy was 0.88. The decision tree accuracy is 0.86. So as we could see, the logistic regression accuracy was a little bit more pretty similar. So the overall accuracy. So I see that with those having a logistic model regression and an overall accuracy of 88.36, where the decision tree was 86.18. I think the logistic regression sensitivity true positive rate was 86.99, where specifically the true negative rate was 89.47. I think the overall accuracy of the regression model is slightly higher. Overall accuracy meaning it correctly classifies the greater proportion of the test cases. The kappa statistic, I think, has had a higher kappa for logistic regression, indicates the better agreement between predictive and actual classes for accounting for chance. So I see that the decision tree model is slightly higher in sensitivity, meaning it's marginally better at correct identifying patients and heart disease. However, the logistic regression has better specificity, meaning it is more accurate to correctly identify patients without heart disease. So with both models performing well, in logistic regression model edges out slightly in overall accuracy and specificity. I think I said it right that time, making it slightly better choice for the data set. So with a higher sensitivity, need to be interpretable vision models, the decision tree will still be appealing, but my final choice may depend on a specific cost and benefits of false positives versus false negatives in the application of this. Ugh.